Okay, good afternoon, everybody. Welcome to this last webinar on robust optimization before the holiday. And it is a pleasure for me to introduce the speaker, and that's Aras Selvi from Imperial College in London. He's a PhD student of Wolfram Wiesemann. His talk is about convex maximization via adjustable robust optimization. So he had a very stressful morning because there were constructions in the building where he lives, but they stopped it now, the drilling, and so we can have this webinar now. So that is perfect. So you're also asked to allowed to ask questions, but I ask you to do that afterwards, so after the presentation. So Aras, the floor is yours.
Thank you so much, Dick, for this kind introduction and for giving me this opportunity to talk about my work here today. And thanks everyone for joining. So I'm going to speak about convex maximization. So this is a problem where we maximize a convex function over some convex constraints. And this is a hard optimization problem, but not from the robust optimization field. However, I'm going to show you that we can very efficiently approximate this problem with the adjustable robust optimization techniques. And this is joint work with Ronnie Bental, Ruud Brekelmans, and Dick den Hertog. And I spent most of my time on this project when I was at Tilburg University. So let me formally define you the convex maximization problem. F is a closed convex function, and we are maximizing f over a convex space U. And U consists of convex constraints, and the objective function f takes a linear input of x. So this is a challenging problem. This is an NP-hard problem, and it is further shown that in very simple cases, such as maximizing a quadratic function over a hypercube, verifying the local optimality of a solution is NP-hard. But we know that every solution, every local or global solution is at an extreme point of the feasible set. That's why one of the main approaches in the literature enumerate the extreme points of the feasible set. But this may not be possible at all. And even if it is possible, it's in general intractable. And the other group of the methods solve a branch and bound algorithm. And the last group does successive approximations, where they iteratively solve some lower or upper bound approximation problems. But there's a common issue with these methods, namely they are problem specific. So soon we will discuss that there are many real life problems that are equivalent to convex maximization problem. And these fields come up with very specific solutions to these specific problems, but these cannot be generalized. And also another issue is that the existing methods are not scalable for large size problems. Some applications of convex maximization. So from graph theory, the max cut problem is an NP-hard problem where we seek for the maximum weighted cut in a weighted network, in a weighted graph. And this is equivalent to convex maximization because the cut value is a quadratic term where the data matrix is the Laplacian matrix of a graph, which is positive semi-definite. So maximizing this convex cut is maximizing a convex function. There are also many machine learning and data science problems that are equivalent to convex maximization. Some examples are semi-supervised machine learning problems or non-negative PCA problem. The economies of scale paradigm is like if you have a cost function with decreasing unit cost with increasing order quantities, this cost function is concave. And minimizing such a cost is maximizing a convex function. It's equivalent. And another example from the robust optimization field is that if you have a constraint that is convex in the uncertain parameter, and if the uncertain parameter lies in a convex space, then to be able to find the worst case parameter realization, we need to solve a convex maximization problem. There are also indirect applications. So these are some other theoretical problems that are equivalent to convex maximization. And the reason why such indirect applications exist is mostly because the convex maximization is hard, but the objective function is convex. And this property is being used in lots of reformulations. For example, DC programming is difference of convex functions optimization, potentially over some convex constraints. Early work shows that this problem is equivalent to a convex maximization problem. Or today, a very famous heuristic method is named convex-concave procedure. And the concave procedure is nothing but finding an efficient solution to a convex maximization problem. There are also lots of integer optimization problem instances that can be reformulated as a continuous but convex maximization problem. Okay, so our idea for convex maximization starts by reformulating the original problem as a robust optimization problem. So the original problem doesn't have any uncertainty, and the hardness is due to its non-convexity. But with the new formulation, we carry this hardness to the convex uncertainty of the robust optimization problem. This is also a hard problem, but we've reformulated further as an adjustable robust optimization problem. And this has some nice features. It has an adjustable variable for each of the original constraints, and we will show you that we are able to approximate this problem efficiently. And solving the final ARO problem will be solving the convex maximization problem. Okay, so in this flowchart, you can see our approach in steps. So please follow my cursor. So we start with the convex maximization problem on top. And then in step 1, we have the robust optimization reformulation. Then by using convex analysis and some duality tricks, in step 2, we get an adjustable robust optimization reformulation. But this is still hard because the adjustable variables appear non-linearly. And in step 3, we deal with the adjustable variables. So if possible at all, we eliminate the adjustable variables analytically. So in these cases, we can find the optimal decision rules. And if it's not possible, we show that we can use linear decision rules to relax the problem. And now that we don't have the adjustable variables after step 3 anymore, in step 4, we derive an upper bound approximation problem to the convex maximization problem. But this is a safe approximation of the ARO constraints. And then by using the literature on ARO, we find a good lower bound on the original problem by using our upper bound solution. Okay, so in the first part, we have single constraint. So here we are maximizing a convex function over a single convex constraint. And the first 2 steps will follow in a general theorem showing that we can have an adjustable robust optimization problem in this case. And I will specifically show you that if the original constraint is a p-norm constraint, we can analytically eliminate the adjustable variable. And finally, for a specific case of geometric maximization over 2-norm and infinity norm problems, I will derive the explicit problems, the approximation problems. Okay, so let me start with step 1. So problem 1 here is the convex maximization problem in the general form. So the feasible set U consists of a single constraint, gx less than or equal to rho. And G is a closed convex function, and we assume that there is a strictly feasible solution. So the equivalent problem is obtained as the following. Instead of maximizing f over the space U in problem 1, we minimize an upper bound tau such that this upper bound is a valid bound for every realization of x. So these two are very straightforward derivation, and it's like equivalent problems. But now problem 2 is like a robust optimization problem because for all x in U can be interpreted as an uncertain parameter, and the main constraint here is convex in terms of the uncertain parameter. This is a semi-infinite constraint, so this is still hard. But in the next step, we derive the adjustable robust optimization reformulation. So just to remind you, the convex conjugate of f is denoted as f star y, which is a maximization problem of a linear term minus the function itself. Okay, now remember that in the previous case, problem 2 is equivalent to the global optimum value of the convex maximization problem. But we have this constraint here. So I take this constraint to 3a. And now we can apply the identity above, namely f is equal to the biconjugate of f when f is closed convex. And by plugging this identity to 3a, we obtain 3b. And now we have semi-infinite constraints. So I take the worst case over x, and we have problem 3c. And if you see, there are like two maximizations in order, so we can swap their orderings. And now we have an outer problem, which is maximization over w, and an inner problem, that is maximization over x. But for a second, if you ignore this problem inside, we have a linear term of w and a concave term, because f conjugate of w is convex, so the negative is concave. So everything except the inner maximization problem is fine right now. But inside, we have a bilinear objective, so w and x are being multiplied. However, if we fix w, this is a linear objective, and x is in a convex set. So this is a convex optimization problem. And in this step, we take the Lagrange duality inside, and after applying a tiny bit of algebra, we obtain 3e. And in 3e inside, now we have a minimization problem over lambda, and here we have a linear term plus the perspective of G conjugate. Okay, now we have for like the worst case W, so we can write for all W in the domain of F conjugate. And instead of the minimum lambda, we can say there exists a lambda such that this constraint is feasible. And in this formulation, for all W can be interpreted as an uncertain parameter, and the lambda is an adjustable variable in this formulation. So now, since we are minimizing tau over this constraint, our general main theorem follows, which says the convex maximization problem has the global optimum value that is equal to the solution, the optimal tau in this problem. And this is minimizing tau over the constraint that we just derived. So here we don't have the variable x anymore. So, but we can also obtain the solution x to the original problem once we solve this problem. And for this purpose, we delve into the duality step. So recall that in 3D, we took Lagrange duality and we obtained 3e. And the details is as the following. So we take this maximization problem, and in 4a, we directly replace the Lagrange dual problem here. And if we take the common lambda term in front of the maximization here, then we have 4b. And the gray highlighted part in 4b is the conjugate of g. And we finally replace this, and we plugged 4c instead of the maximization over x, and we obtained our general theorem. But by using 4b, we can also take the solution x back as well. This is associated with obtaining a lower bound. So I jumped the step of upper bound for a second because that will be problem specific. But assume we solve the ARO problem, maybe a safe approximation, and we get a solution. So we previously showed that problem 5 gives the global optimum value of the original convex maximization problem. And if we plug 4b, this term here, instead of the inner maximization problem of x, we have the second line here. Now, if we knew the optimal decision rule lambda and the worst case parameter w, then solving this gray problem would give us the optimal solution x. But if we somehow take a relaxation of ARO and obtain a feasible lambda bar and w bar, and solving this gray highlighted problem would give us a lower bound. So this x bar will give us a lower bound on the optimal value of the original problem. Now let me completely derive also the upper bound step for a case. So in this case, U consists of a single two-norm constraint. So we are maximizing a closed convex function f over this two-norm constraint. And we just apply the theorem, and it directly gives us problem 6. So we know that problem 6, the tau star here, has the global optimum value of the original convex maximization problem. But in this case, the inner problem, the inner minimization problem over lambda, is a convex optimization problem. So we can just take the first order conditions here, and we can derive an explicit solution for lambda. And in this case, we know that this is the optimal decision rule. So we just eliminated the adjustable variable. If we plug this term back in problem 6, we finally have problem 7, and this is equivalent to a static robust optimization problem. And in this problem, everything except this 2 norm is fine, because these two terms are linear, and minus f conjugate is concave, so maximizing over w is fine. And the ugly term here is the 2 norm, it's convex. But previously, the ugly term was maximizing f, the convex function f, and now this one is less ugly compared to the previous case. And we also know how to deal with the 2 norm, because we know how to approximate the 2 norm efficiently. And let me show you this in the following example. So we are maximizing the log sum x function. This is the geometric function over the 2 norm constraint. And we just showed that in step 3, so just to recall you, step 3 is eliminating or relaxing the adjustable variable, and step 3a is when we can eliminate it. So we eliminated the adjustable variable, and we have this function, this maximization problem, with the 2 norm here. Now we can derive the conjugate of geometric function, which is the negative entropy over its domain. That is the standard m-dimensional simplex. So that is linear. Here we have linear constraints. And now we can relax this 2 norm by taking the reformulation linearization technique, RLT. So in this 2 norm, we have a quadratic term in a square root. So we approximate the quadratic term with a linear term. So the square root of this linear term becomes concave, and we add some extra linear constraints such that this new term approximates the 2 norm as accurately as possible. Now we relax the problem. This is a convex problem. And in the case of log sum x maximization, this is exponential cone-representable. We show that. But this is an upper bound because we just relaxed the 2 norm. And in step 5, after we take our upper bound solution W bar, we can also compute the lambda bar because we know the structure of lambda, the optimal decision rule. And solving this problem over x gives us a lower bound x bar. We discussed that in the step of lower bound, but this is a convex optimization problem, and G is differentiable with an inverse. So we can analytically find that this term here at the end is the lower bound solution. And if you plug this lower bound solution to the original constraint, it is tight. So it shows us that this lower bound is an extreme value solution, which is also desirable because we know that every local or global optimum solution is at an extreme point. So this is the numerical experiment for the case of geometric maximization over a 2 norm constraint. As I told you, our approximation is by solving an upper bound problem that is exponential cone representable. So we use MOSEC here. And MOSEC's exponential cone optimization solver is very efficient. And to get a lower bound solution, we just showed you this is analytical. So this is in 0 seconds. So the time here is the time that it took us to compute the upper bound in seconds. We benchmark our solution with Baron, a global optimization solver, and Nitro, a local optimization solver. And we use Nitro's multiple start feature. So problem 3, I mean, in the original paper, this table is more detailed, but this is a simplified version. So if we focus on problem 3, this has 100 variables and 120 x terms in the logarithm of the objective function. In this case, just with a single starting point, Nitro finds the global optimum value in 1.6 seconds. But Nitro doesn't guarantee global optimality, and we verify it ourselves. Baron has numerical difficulties in geometric function. So Baron is not really usable in this case. On the other hand, our upper bound and lower bound approximations are equal to each other. So we also guarantee global optimality, and it takes only 0.23 seconds. The next problem is problem 9. This is a small problem, but this is a computationally very hard problem. So evaluating log sum x is hard. That's why here the solvers fail, but we again find the global optimum value in 0.24 seconds. So problem 10 has 10,000 variables, so this is a larger problem. And the solvers cannot find any solution in half an hour. We find very tight approximations in 0.29 seconds. And our lower bound is 455.5, and upper bound is 456.5. So these are very close to each other. And in another case where m is larger, this is an interesting case because in problem 12, Nitro can find a solution in half an hour, but this solution is worse than our lower bound solution that we just computed in half a second. We also have a gap with our upper bound, but this is not big, and the whole upper and lower bound approximation works in half a second. So if we instead had box constraints, so what we did was in the previous numerical experiments, we solved the case with a convex maximization over a 2 norm. But if the constraints were box constraints, so if the norm was infinity norm, then we would have a similar approximation. So we can solve that the convex maximization problem is equivalent to problem 8. And this is very similar to the case of 2 norm, but here we had a 2 norm, and now we have 1 norm. So we generalize this result in our paper, and we show that if the original constraint is a p-norm constraint, then this equivalent problem will have the dual norm here. And now, in the box constraint case, we can deal with this 1 norm even without relaxing it. So we can use logical programming, and by introducing some binary variables and adding linear terms, problem 8 becomes mixed integer convex optimization problem. And solving this would solve the convex maximization problem to global optimality. And in an example, we show, again, maximizing the geometric function over a infinity norm constraint. And in this case, we use MOSEX mixed integer exponential cone optimization solver. So although the mixed integer property would make the problem be insolvable in very large cases, we observe that MOSEX solver is very efficient, and thanks to our reformulation, like very reasonable or like big size problems can be solved to global optimality efficiently. Okay, in the second part, we talk about multiple convex constraints. So in this case, we have a convex function, the objective function that we are maximizing, and we have multiple convex constraints. And similarly, we again show that there is an ARO problem that is equivalent to the original problem. And then I will show you that a specific case where the original constraints are linear admits a special form. So namely, the ARO problem becomes linear. So it's an ARLO problem now. And in such problems, we know how to use linear decision rules very efficiently to obtain upper and lower bound approximation problems. And then I will show you the explicit problems to be able to derive upper and lower bounds when the function f is quadratic, geometric, or sum of max linear terms functions. All right, so let me start with the step of ARO reformulation. Problem 9 is the generic problem, which has q many convex constraints, and each constraint is indexed by j. So each function g is closed convex function. And again, we assume that a strictly feasible solution exists. And if we follow our previous theorem with the notation of x in the feasible set, we again have the same result, saying the global optimum value of problem 9 is the minimal tau such that this constraint is valid. And similarly as the previous theorem, we take the Lagrange duality inside. But because we have multiple constraints now, in the second line, we have a minimization problem over q many lambdas. So we have more adjustable variables. And this conjugate here is ugly because this is the conjugate of a function that is sum of every original constraint times a lambda value. So each constraint is multiplied by a single adjustable variable, and this is summed, and we take conjugate. But we can simplify this by taking the Informal convolution operator. That works as the following. So this conjugate here, which is the conjugate of a summation, can be replaced by summation of many conjugates. And each conjugate is the conjugate of a single lambda I times gi with an input of zi. So this is a column vector. And the constraint is that these vectors should sum to A transpose W, which is the original input. And if we minimize this summation of conjugates, then we have the Informal convolution equation. So these are equivalent in this case. And we can also take this lambda I out of the conjugate. And in that case, we should divide the input by lambda I. And now if we plug this to the previous equation here, so inequality here, we have our theorem, which says the convex maximization problem has the same optimal value as the optimal tau in this problem. And this is again an adjustable robust optimization problem where lambdas are adjustable variables. But here the variable z is also adjustable variable and it's of size n times q. But the first constraint, that tau is upper bounding, looks very similar to the previous case, but we have summation over the perspectives here. Also, we have an additional constraint, that is the domain of Informal convolution. But there are cases where we can relax this problem, and I will talk about a special case where our original constraints are linear. So again, the generic convex maximization problem is here. But this time, U is defined by a linear system, dx less than or equal to small d. So this gives a polyhedron. And applying the previous theorem says that the equivalent ARO problem is the following. If you notice here, we don't have the variable z anymore. So here we had z that is of size n times q. But thanks to the domain of the conjugate of the polyhedron, we show that this is simplified. So we don't have z anymore. And the only issue is the minus f conjugate here. But if we lift this term to the uncertainty set, then this whole problem becomes adjustable, robust, linear optimization problem. And now we have an adjustable, robust, linear optimization problem, and there are many methods how to solve this. So a method is the Fourier-Motzkin elimination. With this approach, we can eliminate some or all of the adjustable variables. And I implemented this. It works very well for small size problems. But to be able to approximate large scale problems, we take linear decision rules. So by using linear decision rules, we take a safe approximation of the ARO constraints. And because the ARO problem is a minimization problem, taking the safe approximation gives us an upper bound on the original convex maximization problem. And now we show that this upper bound problem is a convex optimization problem. And its complexity will depend on the f, the function we are maximizing. So specifically, step 4, the upper bound approximation problem, becomes minimizing tau over this system. And in these constraints, we have some non-negativity constraints and the main constraints that are convex and that include the perspective of f. And we can simplify this further. So if f is positively homogeneous, then the perspectives simplify. We don't have the non-negativity constraints anymore, and the variable r is not needed. So this, if we have f, which is positively homogeneous, then this problem even simplifies further. And a small note, in these constraints, if these are equal to 0, the non-negativity constraints, then we have the understanding that the perspectives are defined as the recession functions in this case. Okay, now we solve step 4 and we have an upper bound, and obtaining a lower bound works as the following. So remember that this line on top, this problem, is equivalent to the global optimum value of the convex maximization problem. And if we knew the worst case W, then solving the inner problem would give us the optimal X value. But because we take a safe approximation, we will instead try to find the lower bound X by solving this inner problem for many W values. And so we solved problem 11. We solved the inner problem for many small W bars. And these W's come from a set W bar. And how to generate this W bar set is via the scenario approach from the adjustable robust optimization literature. So here we plug the optimal linear decision rule. And just to remind you, we optimize it here. And after we plug it to the ARO constraints, the original ARO problem, in each constraint, we find the worst case parameter realization of W. And so each of these worst cases are added to W bar in problem 11. And then out of all these X bar values, the best one will give us the best lower bound solution. And now the complexity of steps 4 and 5, so the upper and lower bound problems, are given in this table. If we are maximizing a convex quadratic function over a polyhedron, then the upper bound problem becomes conic quadratic optimization, and the lower bound is just collecting analytically some scenarios. And if we are maximizing the geometric function, then the upper bound and lower bound problems are both exponential cone optimization problems. And if we are maximizing the sum of max linear terms function, then the upper bound is a linear optimization problem, and lower bound is again just analytic scenarios. Now the numerical experiments follow. So in this case, this table is for convex quadratic maximization. And here our benchmarking solver simplex is really powerful because they can solve non-convex quadratic optimization problems with a branch and bound algorithm. And we expect such a branch and bound algorithm would work perfectly in small size problems, and it will start to become less useful in large size problems. And let us check problem 3. Here we have 10 variables and 15 constraints. So this is a small problem. And in 0.17 seconds, we have the globally optimum lower bound, although we don't verify it because our upper bound has some gap here. And simplex also finds the global optimum value in 0.15 seconds. So here simplex works pretty well. But if we keep increasing the problem size, so in problem 6, we have 200 variables and 240 constraints, then our lower bound is globally optimum. And we verified ourselves because the upper bound has some gap. But the whole upper and lower bound computation takes 28 seconds, while simplex needs 466 seconds to compute the global optimum value. And if we keep increasing the problem size, we still solve everything in 35 seconds, but simplex in 1 hour can only find 7,000 as the best value. On the other hand, our lower and upper bounds are around 1.9 million. So there is a huge gap between simplex's solution versus our lower bound and upper bound approximation. Also, I want to note that in our experiments, all of our lower bounds are globally optimum, except problem 7, because we don't know the global optimum value here because simplex does not terminate. So in the next experiment, we are maximizing the sum of max linear terms function. This is a special problem because the solvers reformulate this problem as a mixed integer optimization problem. So this problem, is equivalent to a mixed integer optimization problem. That's why we use Groby as a benchmark solver. But again, because it's a mixed integer problem, in big size problems, we don't expect much from the solver. Okay, let me describe problem 1. N is the variable size, N is 5 here. Size of IK means in each of the max terms, how many potential candidate linear terms are there to be considered as the maximum value, as K is the total number of max terms that is being summed in the objective function. So in the first problem, K is 1, and our upper and lower bounds are equal to each other. And this is not surprising, because we know from the adjustable robust optimization literature that in this case, when K is equal to 1, linear decision rules are optimal. Also, Groby finds the global optimum value very efficiently. But if we increase the problem size, for example, problem number 5, which has 100 variables, we find upper and lower bounds in a total of 20 seconds. And Groby, in 1,000 seconds, can find a solution that is better than our lower bound. But if we restrict Groby, so this restricted column means that we restrict Groby's total runtime to the time that it takes us to solve the problem. Then if we restrict Groby, the best solution it can find is worse than our lower bound. And in problem 13, if we increase the size of ik, then Groby needs to use more integer variables. In this case, the problem gets even more complicated. And in 1,000 seconds, Groby can find 1,000 for the best value, while in just 11 seconds, we find 17,000 lower bound, and our upper bound is 17,500. So once again, we have the same result here. By increasing the size of the problem, we can still efficiently approximate the problem in very short time, and the solvers start to become useless. So this was the end of my numerical experiments, but just to summarize you, the convex maximization problem is a hard optimization problem that doesn't have uncertain parameters, and the difficulty arises from its non-convexity. But with an equivalent ARO problem, we carry the difficulty to its uncertain parameters and the adjustable variables. And now we have many methods in the ARO literature to efficiently approximate such problems. And by using these techniques, we show that we can very efficiently come up with tight bounds on the original problem. And thank you very much for listening to me. And here is a barcode. And if you scan that, it will direct you to the original paper, the version on optimization online. So thank you.
Thank you very much, Aras, for this clear presentation.
Thank you.
Are there any questions?
Dick, I have a question.
Yeah.
Very nice work, Aras. So do you have any insights for what functions f the approach would work particularly well and for which functions f might not?
Yeah, I thought about it, and I worked a bit on that previously. So here we have three problems: quadratic, geometric, and sum of max linear terms. So the performance on quadratic case, when f is quadratic, on the upper bounds is not that tight compared to the other problems. And I believe this has to do something with the domain and the conjugate of these functions. Because, for example, geometric maximization, I didn't even mention the numerical experiments here of that case because it's really impressive. And I think that's because its conjugate is the entropy and its domain is just a standard simplex. So I believe that has to do something with the domain of the conjugate, but I didn't dive in it further. And Dick and Ronnie, Ruth, what is your opinion about this?
So is Ronnie also present? I don't think so. Yeah, so I think I agree with you, Aras. So, but a full answer I also don't have. But I think it has to do with how simple and what the structure is of the domain of the conjugate. Indeed, yeah. But yeah, for me, it's also still a miracle why, for example, the lower bound is almost always the global optimum.
Now, in some examples, the calculating conjugates, I mean, sometimes you cannot do it in closed form. I mean, in the examples that we have, you can do it, but not in general. So as a result, taking derivatives also might not be, you can do it, but it's not a triviality. So can you envision that this method would also work where the conjugate calculation is hard in a way? You don't have it in closed form, so calculating derivatives is only implicit?
Yes, so Aras, or shall I answer it?
Yes, yeah, but I think this has to do about the lower bound we discussed when the constraint was infinity norm, right? But yeah, you can maybe share your opinion, Dick.
Yeah, so I think there are many functions of f for which maybe there's no explicit formula for the conjugate, but we can use all the rules for that. For example, the informal convolution and so on. And then we get an inf again, but that's not a problem. So we can deal with many examples and many functions. So
and I agree with that.
So please give me a function that's not possible. Of course, you can find it, but I think
not natural. Yes.
Yeah.
Yeah.
Other questions?
Dick, may I ask a question?
Yes.
Thank you very much. Yes, thank you very much, Aras. Very nice presentation. I was wondering how, well, typically, if you have a quadratic function, the method most used until now was something like the S-lemma or the approximate S-lemma. And if you have the S-lemma with one constraint, we know that is exact. If you have more than one constraint, we know that it's approximate. How does the method relate to the approximate S-lemma?
So we were dealing with the case where we are maximizing the quadratic function and the constraint is a single quadratic constraint. And in that case, we were comparing our methods with S-lemma because there we were relaxing the adjustable variables and we were looking for the connection between the S-lemma and our approach. But in the problems that I solved, the constraints are linear and the function, the objective function is quadratic. So I don't think that S-lemma is directly relatable to this case. If you also agree.
Yeah. I think you could potentially reformulate it, but yeah, it's fine.
Yeah, we actually had a discussion very recently about this, and we see some connection, but when the constraints are linear, it was not very clear to me.
Okay. Thanks.
Thank you for the question.
Erik de Lage.
Yes. Hi, Aras. Thanks for the talk.
Hello, thank you.
If I understand well, in the case of the quadratic constraint for the uncertainty set, you talk about applying RLT to get an upper bound?
Yeah.
So in the work I did with Amir, we show that the RLT is related to affine decision rules. Like, can you relate back this RLT trick to applying a affine decision rule in the two-stage formulation for the quadratic uncertainty set?
So I applied that here, if you see my screen, to the 2 norm, but we didn't have any adjustable variable here because we know the optimal decision rules here. So I just replaced a 2 norm that is just a static optimization problem. So I don't think this is directly something about the decision rule itself or lambda.
Yeah, because adjustable the adjustable variable has been eliminated before already.
Yeah, we eliminated it by solving this gray problem, but the 2 norm comes from the optimal decision rule as well. So, yeah.
No, I'm thinking like here you eliminate, then you linearize.
Yep.
While you could linearize using an affine decision rule and then reformulate.
And that would be equivalent.
I'm wondering if it's equivalent or not.
No,
I don't know.
I don't think.
To be honest, I always Yeah, I took the optimal decision rule, and it's like whatever we do after using any decision rule wouldn't improve significantly. So, so I don't know. Just because I know the decision rule, the optimal decision rule here, I didn't seek for applying any other decision rules.
Okay, thank you.
Thanks for the question.
Any other questions?
Maybe I take a question. Thanks, Aras, for a very nice presentation. I have two quick questions. First, whether you happen to apply some of the first order method like gradient descent, projected gradient descent, or Frank-Fold to the application?
No, I didn't.
Okay. And then the second question is more, if I noted correctly on your slide number 14.
Yeah.
No, so I noted wrongly. So there you actually choose the W's. At some point you sample from W's scenario approach type.
This one.
Exactly. My question is, how do you choose WIs and how the choice of WIs has an impact on your bounds?
Yes, so let me tell you how it works. So here we have many W bar I values that come from a set bigger W bar. And this here, how we generate this set is directly from the adjustable robust optimization literature. So the cited papers here are from, one is from Hadigiani's paper and the other one is Trevor Zenn's paper. So we basically take this linear decision rule to the ARO problem, the decision rule that's optimized, and each constraint, we take the worst case W realization. And if we take from constraint I, then the worst case W realization is WI here. And so we saw this problem many times for the number of original constraints. And we try these X values one by one. And that's why in the lower bounds, I always report the best lower bound out of all these ones which are tried.
Thank you.
Does that answer your question?
Yes, thank you.
Okay, thank you. Thanks for the question.
Okay, so looking at the time, I think it's time already. So thank you very much, Aras.
Thank you for your attendance, everyone.
And so this is the last webinar before the holiday. We now have holiday, and the next webinar is August 27. And so that webinar will be done by André Gassijn. But first we have holiday, so I wish you a very pleasant holiday. Stay safe and see you then August 27. Thank you very much.
Thank you.
Bye.